All right, sorry about that. I was trying to get the stream going for everybody. So, welcome back. I feel like now we're either at the survivors or maybe the true chemists are the only ones that remain. Because I was trying to figure out, like, who are we missing? So, I don't know, maybe like the engineering people. Welcome, welcome. I know we have one new face, not to pick on you since this is the third quarter of a sequence, so, you're going to stick out, but welcome. I saw your name. Okay, people are online. So if you aren't registered for the class, please register. If you see your friends aren't here, kind of poke on them. I'm trying to, he's just taking it online. I'm just trying to figure out who else we're missing. I thought she was on the roster. I'll give roll. But yeah, check on your friends. Encourage them to take the third quarter, even if their program doesn't require it. Like, I'm sure that's why some of the engineering people are missing. I don't think that's a wise choice. Uh, Again, you never know what's going to happen, or you could transfer out of state, or, anything. So I would complete the series, but, I'm glad y'all are here. So we have homework, lab, pretty much the same deal as before. So I'll go through the syllabus. I do have something exciting though to announce. So I will be fixing your syllabus on that note, but it's a positive development. So we have, just making sure that's correct syllabus. Blah, blah, blah. Usual things, we'll be continuing with our buffers. So for those of you who aren't used to our format, right, usually we lecture for 2 hours, and then for our class/recitation period on Thursday, we lecture for the first hour, and then do a quiz over the previous week, or go out over anything. So that's your time to ask questions, work on homework. So use it wisely. And then this week we'll just have our welcome assignment. So make sure you get that taken care of, especially if you're joining online. And then other things to look forward to. So looking at our syllabus, we have our labs. So starting with titration curves, acid deposition, but then I'll have to adjust some things. So I'm not sure if I'll keep this week blank. But we will have a Oregon Caves field trip this year, so that is on the schedule. I don't know if it'll be this week, though, but that is exciting. That I did actually just receive confirmation that they are open, because last year there was a whole thing where the caves got shut down. The federal funding didn't help, yada, yada, yada. So we didn't do a field trip last year. So we're going to do one this year. It's going to be optional. That's just per kind of policy and procedure. But yeah, that's kind of exciting. So tentative, so date to be determined. And so basically how that will work is usually we go on a Thursday and we don't go to class that day. Like that is our class lab, right? So instead of spending the day in lecture lab, we'll use the time to drive over to the Oregon Caves. They take us on a nice little tour. And then obviously you're free to go about your day. So I'm just waiting for confirmation, and as soon as I know that, I will, of course, communicate that to y'all. But then there will be an alternative assignment. So if you can't make it, work, or I don't know, you just don't want to go to the caves, which is fine, there's a video, of course, so you can watch and then write a small, one-page essay for that. But I do encourage you to go on the Oregon Caves, and then I'm putting this out there. So I can't facilitate with right arranging or really encourage that. So that's kind of on your own to get there. So that's why I'm kind of putting it on your radar so you can start thinking about transportation now, because it is out by Cave Junction. I don't know. Have people been to the caves or? So yeah, a few people have, but it's pretty fun. When we went 2 years ago, we actually saw a teeny bat, so that was really cool. And of course, there's usually see a few cave spiders, which are pretty cool. So yeah, I'm pretty excited that that's back on the calendar. And yeah, because I've been doing just some light reading. I know I forgot what John Day Camp. Yeah, there's so many interesting geological formations in Oregon and so many caves. So yeah, if you get the chance to day trip it, definitely do so. And obviously they'll go over the cave chemistry. So just be aware that there could be shuffling of these lab assignments as we get our official field trip date down. And then we do have some fun experiments. So this one pot reaction is another good one. And then at the end, we'll do an aspirin synthesis. If we need another lab, we can always throw in a lab. I don't think we'll need it this quarter, but kind of an optional thing. So what we did last year, since we didn't do the field trip, and I failed in arranging an alternative, is we did an ice cream lab. And so part of the lab was like comparing, the rock salt and how the texture of the ice cream comes out versus like a liquid nitrogen ice cream, and then you could also compare like different milks. So that was kind of what their lab consisted of. So we could throw that in as like a fun lab, or just like, maybe not a formal lab. But yeah, I'm just kind of like throwing that out there as something else that we could kind of play with or do if we want to throw in a lab. And then something else that we're looking forward to this quarter. So I graded your papers on just more like completion and effort for last quarter. And then I need a bit more time to sit with them so I can like actually read through them, because it takes me like a few reads to kind of actually give you meaningful feedback. So my goal is to kind of return the papers probably next week with feedback for you. And then, of course, you'll just be working to build that into a final paper, so 5 pages. And so, again, not to pick on you, so you haven't started, but you're not at too much of a disadvantage. It's only a 5-page paper, so yeah, I can obviously help you to get that off the ground. But otherwise, other people, you're just kind of building. And that's the good thing, too, is you're graded off of like what you're building from. So obviously, if you're starting from 0, I'll take that into account. Other people, are starting from like much more polished, finished drafts. So then I'm going to want to, I kind of expect that to obviously carry. And obviously, if you already have like a really good final product, like I'll probably, note that as well, but offer still tweaks and suggestions as we try to continue to develop our writing skills that we've been working on. And then, so with that, we'll have poster presentations, which is really fun. So that will be in lieu of our final exam. So I did cancel an exam. So there's going to be no lab final this quarter. See, more good news. See, so no lab final. So yeah, so that's good, right? No stress. And I mean, I like to think of it as a poster symposium party at the end. So we'll do poster presentations. We'll probably ideally combine into Tuesday or Thursday. If somebody can't make it due to work, we can always work that out or figure out some alternate arrangement or something. But the whole deal, and I'm just explaining it now so people also don't get overstressed about it. So how kind of the poster presentation symposium works is it's supposed to mimic what you would do at a poster presentation at a conference. You'll kind of stand by your poster, you have it all done up, and then the other half of the class will kind of walk around and you can give your little spiel and people can ask questions, kind of give, a light presentation. And so that's pretty common, if you were to go to a professional conference for chemistry, you stand there and, people walk around and ask you questions. So that's just good practice. And the whole idea is that it's more low stake presentation. So I encourage everyone to do it. I know over the years, some people have had presentation accommodations or disability things, but I encourage people still just do it. That's the whole point. It's fun, it's practice, it's just kind of getting you in the rhythm of presenting, as opposed to standing you in front of the class and making you give a formal presentation. The poster is supposed to be fun and loose and more of a dialogue. And so that's good. And then I always bring kind of snacks and stuff. So again, we can have like a little party, we'll call it. And then of course we do have to have a final exam. So we will still have our final exam on Thursday, but it shouldn't be too bad. And yeah, again, you're kind of the survivors at this point, uh, which makes the curve a little more generous as well. So I take everything into consideration. So I'm not going to destroy people. Question. It's always on the Thursday. I don't. The dates could be a little wonky. I don't know. I try to like auto shift everything too. Hopefully that worked. This new Blackboard Ultra, I swear, like plays less well than the just regular Blackboard. So much for Ultra. All right. Any thoughts, questions, ideas? Oh, and then just to go over everything, I know we have a lot of returners, and I don't know how I do this in not crazy view. I just wanted to remind everybody, where are our assignments? There we go, assignments due. So just don't forget about the reading questions. So some people historically forget about these. And so this is the only assignment that's in Blackboard online, but everything I give paper, but there are, of course, copies on Blackboard of all the assignments. All right, I think, any other announcements? Oh, I forgot my name, obviously, but you guys know me. I only have to worry about that with my Chem 104 class. So I put my email. So yeah, just call me Marissa, please. So save the doctor titles for doctors. All right. So as usual, I don't take attendance, but I will take it formally. I know a few people have emailed me that they are alive and attending, but just sick. So that's fine. If you haven't checked in yet and you're online, just check in with me so I know that you're present and accounted for. Oops, sorry. While I was talking, my rogue logged me out. Sorry, give me 1 second. All right, and then I'm going to mute on the stream just so I don't have everybody's name on stream. joining the third quarter of a chemistry sequence generally isn't too popular. But yeah, you and I will chat just to make sure that you're on board because we're kind of well, can I where'd you come from? Oh, okay. So then you should be okay. Just checking that. I mean, the whole point of the whole Common Course numbering is that, right, you could switch to any school in Oregon, but, let's not test that theory too much in practice. All right, anyways, so, right, we left off on kind of acids and bases, just trying to clear the cobwebs. I know you guys only had a week off, but I guess we can forget a lot in a week when it comes to chemistry. So yeah, we were looking at acids and bases, and then we were starting to talk about buffers, and then remember, right, had been looking at equilibrium expressions. I was kind of, well, I don't know. I'm just trying to clear the cobwebs for a second. Like, okay, yeah, we're looking at these equilibrium expressions, right? We were calculating K, which starts to get us into pKa and all that. So if we need a refresher, I was just trying to like zoom. Also, yeah, so please slow me down. I know that's like the one thing I should work on is kind of going through the math a little slower. So I will try to be better about that, but again, you can always remind me or flag me down or like, hey, can we talk about something from last quarter again, since everything does kind of build. And so we're looking at antifreeze, which, by the way, I don't know if people know that, like those snow globes, usually that's actually the chemical they contain is antifreeze. And then, of course, if you have pets, that's a huge concern, right, if your snow globe ever breaks. And so this is explaining why that this is such a danger to animals, especially cats, from what I'm told. And so this is from it being sweet tasting, so the cat will certainly come over and start licking it. And then this, of course, results in symptoms like drunkenness, and then it's metabolized to this glycolic acid. And so the problem with this is, again, of course, and it doesn't take much to kill a small cat, but what happens is this glycolic acid, right, overwhelms the buffering ability of our bicarbonate in the blood. And of course, we remember that blood is a tightly controlled pH buffer system. And so, right, we'll of course talk about the buffering ability in this chapter, but you can, of course, overwhelm the acid, right, essentially doing a complete neutralization reaction such that, right, there's nothing really that can go back to equilibrium. And so that causes the blood pH to drop dangerously. And then, of course, that affects its ability to carry O2. And so this results in acidosis. So I'm not sure if this applies to cats now or what happens, but I assume that this would also somewhat apply where you give them ethyl alcohol, which has a higher affinity for the enzyme. And I believe this is also the treatment for like methanol poisoning in people, where you give them ethyl alcohol. And so that hopefully, since it has a higher affinity, right, so thinking back to binding constants, so it has a higher binding affinity for the enzyme, so hopefully, right, it can release that toxic. And that's really like the fundamental way like any sort of detoxin works, is it just either has to like bind more or kind of bind the toxin more, and it's always this competing thing, which, works pretty slowly, so that's why it's hard to cure like mercury poisoning or anything like that. I mean, there's all sorts of chelating agents which people try, but all right, so then we're going to be, like I said, we looked at it, but we'll be continuing with our buffer solutions. And so a buffer solution is just defined as a solution that resists changes in pH when our acid or base is added to the solution. And so again, we'll go through all the math, right? So basically, we'll do the acid or base reaction, right? So kind of we'll have our initial conditions, basically like before they react, right? If we could just magically pause them for a second, okay, that's what we're starting with. Then neutralization reaction, and then of course, right, kind of change equilibrium conditions. And then just a reminder on how to construct our buffer solution. And so our buffer, we said, has to contain our weak acid and a conjugate base. So what would be an example of that? Yeah, so acetic acid. And then what's the conjugate base then? Yeah, so acetate, and then pick a counter ion. So it doesn't matter, I'll just put sodium. And I put in parentheses because, again, right, sodium, potassium, lithium, all those would be fine. And then, so of course, we could also do a weak base and its conjugate acid. So what's kind of our classic weak base, we said? So ammonia, perfect. And then what's our conjugate acid? Yeah, so NH4, so ammonium. And then I'll put, well, that parentheses looks bad, but like ammonium chloride, for example. Again, just picking a neutral salt. So you wouldn't want to pick ammonium fluoride, but all the rest would be okay, right? Ammonium bromide. But I assume chloride's the cheapest. At least that would be my guess. And then, of course, like we mentioned, blood is a natural buffer system. So it's our carbonic acid and our bicarbonate ion. And again, that keeps our blood at a tight pH. And then, so we kind of went over it this term, but again, just kind of a refresher, clearing out the cobwebs. So like we said, okay, again, we have to mix our acid and our conjugate base. And so again, this is kind of, right, a refresher. So just kind of reminding us, all right, if we have a strong base added, right, we do our neutralization. The base is, of course, going to react with our acid component. And then again, key point is that it's making our conjugate base as well in the reaction, right? And then, of course, the caveat is, again, that the amount of sodium hydroxide moles has to be less, right, than the moles of acetic acid present, right? Because otherwise, obviously, that will overwhelm it, and we'll approach those scenarios, right, as we get there. So basically, what we find is that there'll be a certain treatment kind of before we hit the equivalence point, right? So there's a way that we calculate our pH. Then we have the equivalence point, which we'll look at, right, because there's a few things to consider. And then we'll have, right, past the equivalence point, where now it's just basically, again, if you were overwhelming it with sodium hydroxide, then it'd basically be just a base reaction, right, and getting the pH of whatever base is left over from your reaction. And so we'll go over all that math. And then again, just a reminder, so same thing, we add our acid, it's going to react with your base component, making your conjugate acid there. Maybe that would help to remind it. So we could write A or HA for convention, right, to kind of remind ourselves of the components. And again, same caveat, so your HCl cannot overwhelm your base, otherwise then we're either looking at our neutral scenario where they're equal, or again past that, so past the equilibrium, so then it'd be treated as more of a strong acid case. All right, so we blah, blah, blah. Let's see. So, of course, we have Le Chatelet's principle. And so this is kind of just reiterating this. And so then we'll look at this common ion effect. So this will come up both with pH, but then we'll kind of see it similarly in solubility. And so all it's reminding us is that, of course, if we add something with the same ion, right, it will affect our pH, right? So all it's saying, okay, we have our salt, so we have our sodium acetate in this case, so that contains our conjugate base, and of course that's going to have an influence on the equilibrium. So again, just kind of demonstrating, and this is just reiterating what we went over last quarter. So like I said, if anyone needs a deeper refresher, we can always go back, ask questions, right? That's kind of the nice thing. I mean, I want everybody in the class as possible, but at least like hopefully as we shrink down, you should feel a little more comfortable asking questions. Plus, you guys have known me for almost a year now, so yeah, I mean, other advantage of community college, at least you're not dealing with a new instructor here. But anyway, so we're just seeing, okay, we're purely acetic acid here, so weak acid, right? We have our pH. Of course, right, you're kind of thinking in the back of your mind about that pKa relationship. Remember how to solve pH from that. And we can always do a refresher if we need. And then, okay, common ion effect. So it's just reminding us, yes, sodium acetate. And this is basically saying that this salt is basic, right? Like it's kind of saying the same thing. So we could ask this question in another way, like is this salt acidic or basic? And then, okay, well, it's basic, right? Because it's acetate. And again, it can react with water, reform our acid, and make hydroxide, so formerly a basic salt. And then we see that in the pH, right? So 8.9. And then obviously it's not a super strong base. There's equilibrium. Again, we can calculate that. So we're getting there. We're marching there slowly. But yeah, so just experimentally, so basic. And then, of course, mixing them, then we have our buffer. And then, so we'll prove it later mathematically. But just kind of notice, and if you happen to remember Henderson-Hasselbalch, then that might be apparent as well. But looking at this, so they have the same molarity of acetic acid as they do their conjugate base, their sodium acetate. And so when this is the case, when your acid equals your base ions, then your pH is equal to your pKa there. And so if you remember Henderson-Hasselbalch, right, you would just take the log of 1, which is 0. So that's how it works out formula-wise. But we'll go through, like I said, with the rice table and see that as well. So you can just kind of see that again. Well, actually, we'll do it right now. So, of course, right, I cheated verbally. And so we had Henderson-Hasselbalch. And maybe I should write it, right? So let's just remind ourselves what's going on and have some context. So last quarter, or last term, we introduced our Henderson-Hasselbalch equation, which was our pH equals our pKa plus our log of our base over our acid. But we did say that there was a small caveat to this formula, if we remember. And so this, if we recall, made that 5% assumption. So, right, we assumed that the change was less than 5% when it came to using that formula. And that was fine. So like I said, right, we introduced it last term. But what we want to do this quarter, and we will revisit some of the pH stuff. I know that came up as a question because there were some tricky pH questions from last quarter that we really didn't address that are actually more appropriate for chapter 21. So we'll kind of revisit those as well. But now we don't want to cheat with this, so we want to set it up using our rice tables and calculate this. And so let's go ahead and do that. And we know our pKa, and this is just looking this up, is 4.74. And so again, you might have a small discrepancy in this value. And I have, well, actually, let me double check that that works. So remember, we can go from pKa to Ka. So 10 to the power of negative 4.75. And that gives me a slightly different answer from what probably I looked up on the internet. I guess it's close enough with rounding. So the value I have from the internet is like 1.82. I'll just round it to 1.8 then for our purposes. So about 1.8 times 10 to the negative fifth. So again, right, small discrepancies could happen. And so now let's set up our rice table. So that's kind of the nice thing, is everything's basically the same as before. And so let's just set up our reaction. And so that's going to be our acid plus our water gives us our hydronium concentration. So you could abbreviate as H+, plus our conjugate base, acetate. And then just kind of recall that we're looking at our reaction of our acid with water, right? Because we're given this Ka, right? So that's what that is describing, right? So we're not looking at like the reverse of Kb right now. I just want to make sure we're all on the same page with that. And then, so right now we have our initial conditions. And so again, just kind of nothing's happened. Just pretend that they haven't disassociated. And so just reading off our initial values. So we have 0.1 molar in our acid. And then we said we started with 0.1 molar in our conjugate base. And again, this is like instantly freezing it before anything is disassociated. And so now we have to predict which way it's going to shift. So we weren't given any K values in this case. But there's a small hint in that, from what I keep saying, right? Nothing's disassociated. So we need to form some hydronium, right? So we don't know how much will be formed. But that means for our change, so of course some of this will be disassociating, so minus x. Again, we don't know how much, right? Again, our Ka dictates how much. We'll quantify this. And then, so this will be plus x, and then plus x, and then of course equilibrium. So 0.1 minus x plus x, 0.1 plus x. All right, so just stopping there for a second. So does this feel good to everybody? We remember? Okay. And then, so Ka, so products over reactants, and again, getting rid of water. So that's our hydronium, which I got a little lazy and wrote as H plus there, times our conjugate base over our still conjugated acid, right? Again, equals our Ka value, which I'm rounding to 1.8 times 10. Well, I'll keep a sig fig for a good measure. Times 10 to the negative fifth. And then, of course, substitute in our values. So x, 0.1 plus x, and then minus x. And so now would be a good time to do that assumption. So assume that x is less than 5%. And this is probably a safe assumption since this is 10 to the negative fifth. So probably safe. And so now that helps us greatly, right, get x. So that makes our algebra a lot easier. So let's rewrite that. So now we have x times 0.1 over 0.1 equals 1.8 times 10 to the negative fifth. And, okay, so now that made it really easy. So x equals 1.8 times 10 to the negative fifth. And then now we can go back, right, because it wanted us to solve for pH. So then negative log of x, so that's equal to our H plus concentration. And you can probably already guess the answer, right, because now we've gone back and forth, really, from pKa to Ka. And now we're really back at our starting answer. And so negative log of 1.8 times 10 to the negative fifth, of course, gives us, right, what we started with for the pKa. So we just proved our Henderson-Hasselbalch equation here, right? And so again, notice, okay, if the base and the acid concentration are the same, that cancels out, and again, pH equals pKa there. Oops. So questions about that one?
So you said what has to be equal for the pKa to be the same as the pH?
The concentrations of your conjugate acid and your conjugate base. So yeah, we can rewrite that. So just to kind of go full circle. So then, right, so let's just say when making a buffer, because this is always a good starting point for a buffer. Like that's kind of the point, because right, like let's just say you're in the lab and like, well, what buffer do I want to make, or like where do I start? And so this is kind of like a good starting point. So if your weak acid equals your conjugate base, then your pH equals your pKa. And then again, I'll just rewrite our Henderson-Hasselbalch just so we can see that again. And so if we plug it in for our case, so now we can do it one more time. So pKa was about 4.74. Again, just be consistent, otherwise you'll be slightly off with the rounding, what pKa and Ka you use. But then plus our log, so then we said 0.1 over 0.1, so as long as they're the same, so it doesn't matter, right? But they're always, and then I'll just put in the calculator so we can all see. So of course the log of 1 is 0. And so then we get our pH equals 4.74 there. And so I just added that explanation, right? So again, if they're equal, that means you're trying to take the log of 1, which is 0. And so again, right, that's your kind of starting place for a buffer. So if you're in the lab, what do I do? How should I make a buffer? Well, start with equal components, right? Kind of start around your pKa, since that'll be your pH. And then, well, where do we go from here if you were to need to modify your pH? Sorry, I lost my notes on the side there. There we go. So, okay, Henderson-Hasselbalch. So now we've seen this. Okay, so now I'll skip this probably. And so this is where we want to be for this chapter. So this is what this chapter is asking. is, well, how do we solve for the pH then, right? We have this nice Henderson-Hasselbalch, which is obviously pretty convenient, or the ice, which, I mean, I still like our rice table, and let's change it. Everybody likes happy rice, much better. But the thing is, so your ice or your rice table can be used under all conditions. So that's really the key, right? So if you're ever unsure of what to do, fall back on your rice table. And so, like we mentioned last quarter, our Henderson-Hasselbalch is only true when we have our X is small approximation. And then this is going to be when we have initial concentrations that are not very dilute. So very dilute, probably like beyond 10 to the negative 3 would be like dilute. And then you're probably going to want to, again, use the full ice table. And then you can use it, like we said, when the Ka is pretty small, right? We've kind of seen that, again, kind of the 10 to the third, 10 to the fourth difference of magnitude. So that's pretty safe. And that usually means, right, your X is small approximation is valid. But again, we'll find that our rice is useful. And then, so the other thing, so this is, again, another caveat. Sometimes I feel like the 100 is cutting it a little too close, so it may not always work out. So again, you always have to double check your X percent. But just saying, so your initial acid and salt concentrations should be 100 to 1,000 times larger than your Ka value. So then that's just telling you, again, where your X is small will be valid. But I'm going to say, right, still double check. All right, so let's look at this equation, or this problem here. And so go ahead and compare the two methods. So do it with the rice table, because it's still good practice to do the rice table, and then compare it with Henderson-Hasselbalch. Sorry, let me go back. So question is, right, what's the reaction? But think again, what is the Ka saying, right? It's the dissociation. So that's the reaction that you're doing, right? So that's just like your definition of your Ka expression, is that it's, in this case, and I'll start sketching it out, your benzoic acid plus water And again, write that dissociation. So we remember, again, the definition of an acid is that it makes some amount of hydronium. And then, of course, our conjugate benzoate. So good. All right, so I'll give you guys maybe another minute or so to poke with it on your own. All right, so let's see how we're doing. So again, initial conditions, and again, just make sure you can identify, okay, well, who's my acid, right? So again, benzoic acid, so 0.05 molar, and then our conjugate base species, so sodium benzoate here, so 0.150 molar. And again, just double checking so nothing is in two equivalents or anything, so 1-to-1 ratio for our dissociation, so that's good. And so now looking at our change, so again, right, we're imagining our scenario where there's been no dissociation, so now some amount will dissociate. We have to determine, again, how much. So minus x, trying to figure out how much hydronium is formed, right, for our pH, and then plus x. So then equilibrium, so 0.05 minus x plus x, 0.15 plus x. And so probably we can make our 5% approximation is what I'm going to guess before I get there. So we were given our Ka, so 6.5 times 10 to the negative fifth, so equals, I'll write it out, so H plus times conjugate base over acid, so equals, plug in variables, so x, 0.15 plus x over 0.05 minus x. And so again, just looking at these values, looking at this, we can probably make our 5% assumption. And that will really help us. And so now we have 6.5 times 10 to the negative fifth equals x times 0.15 over 0.05. And so I'll just plug it into the calculator. So 0.15 divided by 0.05. So 3, so 6.5 times 10 to the negative fifth equals 3x. And so then we should get this value for x. So do we all get that roughly? And then, so now we can get our pH. So x equals 2.16 times 10 to the negative fifth. And again, right, pH, the X was equal to our hydronium concentration. So plug that in to our calculator. So now we have a pH of 4.67. And then did we have a chance to throw that into Henderson-Hasselbalch? So if you're quick with the math, you'll just the formula. Yeah, so then the next step, and so we'll do this real quick before we take a little break. So now let's compare to Henderson-Hasselbalch. And so we were not given the pKa, right, but we can quickly calculate it. And so we're given our pH is equal to our pKa plus our log of base over acid. And so again, just don't mix up who's the base, who's the acid. And so my pKa is equal to 10 to the power of the, oh, sorry, wrong way. pH. Sorry, negative log. pKa equals our negative log of our Ka. So let's get that. So negative log of 6.5 times 10 to the negative fifth. And again, if you look this up, like if you were practicing this on your own, I always expect some sort of minor discrepancy. So about a pKa of 4. I'm just going to round it to 4.2. I'm curious what Google would tell us. Although we probably shouldn't round. But let's check this out. So now plugging this in, so pH is equal to about 4.2 plus our log, and then our base, again, was the sodium benzoate, so 0.15 over 0.05. And so I have a feeling, well, if I use this value, it'll come out more precise. So if you round like I did, it might be off a tad. So, right, about 4.6. If I do 4.2, let's see how bad it is with rounding. I guess I could have just calculated the log of 0.15. So, again, right, minor discrepancies with rounding. So that's what the log of 0.15 over 0.05 is. But we still get right around the same pH of about 4.67 there. Again, with minor rounding issues. So that looks pretty good there. Questions on this so far? So let's go ahead and take our 10-minute break then, especially after all that math. Did we all make it back? Oh, we're still waiting. We'll give people another minute. I mean, no, I just heard about butterflies, but it's like I just squished two caterpillars over spring break alone. So I didn't mean to. Like one, was on it was a sidewalk, and yeah, the other got caught in like the gardening rake. But I mean, we studied it scientifically with my children. Yeah, like yeah, yeah. All right, let's come back from break. So there was a question over the break, and then I thought we might as well leave it up here for a second. So I just wanted to prove with the calculator that making the 5% assumption, right, gives us just about the same answer for that last one. And of course, right, we don't want to do the painful algebra over here of distributing and blah, blah, blah. And so you can look at Wolfram Alpha laying it out in different alternative forms, but yeah, so that again just kind of hopefully makes you feel better about the 5% assumption and why it works. And then again, right, you're more than welcome to work out the full algebra if you need some excitement in your life, but all right, so let's keep practicing. So let's just continue with this one. So again, pH of our buffer solution, and then, right, try both methods. So maybe you want to do Henderson-Hasselbalch first, just so you're like, okay, I want to just know the answer. But then practice the rice table, because again, you want to be comfortable with the rice table for later, even if, on an exam, you're more than welcome to just jump to Henderson-Hasselbalch, unless, of course, it's stated explicitly. Sorry, I had it on mute apparently. I don't know how long I had it on mute. My bad. So then 0.5 minus x plus x there. So now we get equilibrium. And so now we're at our pKb expression. Oh, sorry, I got distracted. It should just be minus x. And so now, right, so Kb expression. So now we have our pKb expression. So 0.2 plus x times x over 0.5 minus x is equal to our pKb, or our Kb, excuse me, our Kb, which they didn't give, but we can calculate, right? So 10 to the power of negative 4.75 here. So that's our constant. So 1.77 times 10 to the negative fifth. And so we'll make our 5% assumption again. And so now math is coming together. So we have 0.2 over 0.5 times x is equal to this number. So then we get this answer, right? But then this is our hydroxide concentration. So we can calculate our POH. So, right, POH is equal to the negative log of x. Oh, and I did the same thing again where I didn't write what x was. So 4.425 times 10 to the negative fifth. So negative log. So then that's my POH. So 4.35. So now we can find our pH. And so we got, right, just about the same answer. So 9.65 there. All right, so I just wanted you to have that. So like we saw, right, Henderson-Hasselbalch is probably the easier way to go, faster way to go for your tests. But it was still good to sketch out this Rice method and again compare the reaction, because what I want you guys to feel comfortable is with, okay, if you're given pKa, pKb, do you know what reaction that is describing, right? Because they could be mean and give you pKb of an acid or something, right? And then you might get kind of confused. So what we're thinking is like, okay, what is it saying? Like, what are we reacting? What are we starting with? And so, right, again, our pKb equilibrium is our base reacting with our water to give our conjugate acid and then form our hydroxide. So again, that's always like your key thing. So you're thinking, okay, my pKa gives us hydronium. My pKa should give me my OH. And then, of course, proceed from there. Okay, so questions about that so far? And so now let's take the next step in this. And so now it asks us to basically do our reaction part. Oops. So calculate the pH then of a 1 liter solution if 0.01 moles of solid sodium hydroxide were added to the original buffer solution. Okay, so now we're kind of thinking about the new information that's given. And so now kind of think about how our calculations are going to be just a little bit different, right? So we're just working in pure molarity here, but notice we're going to have to switch to moles, right? Since we're talking about moles. So we'll switch to moles, so we'll have to calculate that given our volumes and our molarity. So we'll start with our initial moles. So just kind of mentally outlining what we're going to do. And then we'll do the reaction, and then we'll go from there. All right, so let's do this together. And so now we're setting up, again, our reaction and what's going on. And so, okay, if we're adding, so the first question, maybe can I recopy this for us? Let's see if this is a text. It is, yay. Okay. All right, so looking at this, our first question is, well, what part of our buffer is the sodium hydroxide reacting with? So go back to your problem. Which is your acid in this? Excellent. So write the ammonium chloride. So let's set that up. So that's the beginning of our R of our reaction. So okay, so that's going to be sodium hydroxide plus ammonium chloride, and then that's going to react to give us, so neutralization reaction, so we're given sodium chloride, and then we'll reform to make, right, so technically make ammonium hydroxide, which gives us ammonium, right, in solution. So I'm just going to write it as such. So that's our reaction here. And so then we have our initial conditions. And so now I'll put in moles. And so now let's calculate our moles. And so it said we added 0.01 moles of solid NaOH. And then, so now let's go back. So we're going to have to do a little bit of math here. So we were given a 0.2 molar solution of ammonium chloride. It said to assume 1 liter. So let's do, I'll just kind of sketch it out in case people need to clear our cobwebs. So we said we had a 0.2 molar solution. So that's moles per liter. And then we have 1 liter. So then that leaves us with 0.2 moles to begin with of our ammonium chloride. And then we haven't made any sodium chloride yet. There's no indication of that. And then, right, we should sketch out our beginning amount of ammonia, though. So we don't want to forget about that. And so that, so let me calculate it. So 0.5 molarity. So again, same thing. We're assuming a liter, so 0.5 moles per liter, so times 1 liter. And so I'm just kind of putting this to the side, so kind of 0.5 moles here, because again, right, we want to keep track of our acid and then our respective conjugate base, right? That's the whole point of the buffer solution, is that we should be forming our base, or vice versa. Okay, so now we're ready to do the reaction or the change, right? So our change is basically our reaction. And sometimes with these, this kind of becomes like change plus equilibrium, right? So like, have to calculate our new values. Okay, so our sodium hydroxide, so it has fewer moles than our ammonium chloride, right? So it's going to be completely consumed. And then, so our 0.01, sorry, I wrote molarity, but that's, I'm saying moles, sorry. Let me rewrite that. Moles. So react, right? So that means it's going to react with this. So 0.2 minus 0.01 leaves us with 0.19 moles. And then, don't really care about the sodium chloride right now. But, I mean, we would make, right, 0.01 moles. But, again, not really relevant. And then we make 0.10 moles of our ammonia. Right, so from our mole ratio, so this reacts 1 to 1, so we consume all of this, make 0.01 moles of ammonia, sorry. I was going to say ammonium hydroxide, but ammonia, let's just say ammonia for clarity. And then, so that means, I'll just kind of rewrite this as equilibrium. So we don't have this. We have 0.19 moles of ammonium chloride. That doesn't matter. And then we have 0.51 moles of our ammonium hydroxide. And then now we're probably safe to plug it into Henderson-Hasselbalch here. But let's just keep something in mind. So it's not going to matter for this case, but again, I just always want you to be cognizant about it. And so we're going to right plug into HH now. That'll be easier. And so we'll do our starting point. But just recall, right, usually you're given this in molarity, right? So you have moles over liters. And so technically we should rewrite this over liters. Of course, it's over 1 here. So that's something that we're going to have to keep in mind moving forward. So sometimes, right, if you're adding a liquid reagent, well, you want to calculate the total volume. But generally, it doesn't matter, right, because your total volume is going to cancel out anyways. Does that make sense to everybody, right? So we're going to have 0.19 moles. So, right, normally you'd plug in molarity, so over, I'm just going to put liters. And then they're in the same solution, though, so 0.51 moles over liters. So that's why I'm just kind of not worrying about the volume. But just keep it in mind, right? Because, I mean, chemistry, never sure what scenario we might see. So it might be relevant later where we want to keep track of this volume. So I'm just kind of like putting that out there. But we can otherwise move forward, right, since it's going to cancel. And so now I'm going to refer back to here where we had solved for our pKa, right? So pH equals 9.25 plus my log, and now we can just plug in these mole values. So base over acid species. And let's get our new pH. And so that gives us a pH of about 9.68. Question? Just kind of reflect on that. Does that feel okay to people? And question? Oh, because this is the same. Yeah, I just, right, so ammonium plus OH, right, is technically ammonium in solution. So yeah, I just didn't like rewrite that again. But that's why I was kind of like showing both, because if you do the double displacement, you get uh, ammonium hydroxide, right? But again, that's the same thing as ammonia. But yeah, it's just easier to see it in that conjugate acid, conjugate base relationship. Or I should have said, sorry, conjugate acid base relationship. Yeah. So the so the change is basically like our acid base reaction. And so all we did, right, once we converted our base to our point zero 0.01, we're basically doing like our stoichiometry, right? So they're in a 1-to-1 mole ratio. So if I have 0.01 moles of NaOH, it's going to react with 0.01 moles of our sodium hydroxide. Maybe I didn't write that very well. So I probably should have just written our change as minus -0.01. Maybe that's not helping. So minus -0.01 moles, right? So consumed by NaOH. Sorry, I kind of jumped. So right, that's subtracting, that's adding that same stoichiometric amount, right? You're just being consistent with the stoichiometry there. Does that clarify? And so that leads us, though, nicely to this next position. And so, right, we're saying, what's our kind of buffering capacity and range? And so looking at this is kind of, right, teasing, and we're kind of seeing, well, again, we can overwhelm our acid, but let's look at also, like, how do we make the best buffer? And so we have these kind of general rules and guidelines, and of course we can kind of mathematically go over why that's so. And right, again, a good buffer can neutralize and kind of mitigate, right, the pH effects of a small amount of acid or base. But again, there is a limit, like we are seeing or could see if we were to take this equation up here to the next step, which we will eventually. We're getting there. We're getting there in this chapter. And so we have our buffering range is our pH range at which the buffer is effective. We have our buffering capacity, which is just our amount of acid or base that can be neutralized. And so, of course, this depends on two factors, which I think it's pretty self-explanatory, right? We need our relative amounts of acid and base. So we, again, kind of thinking back to Henderson-Hasselbalch. I'll just kind of, right. And again, we said our starting point is generally our pKa, and okay, that gives us a relative starting point. But then, of course, right, the absolute concentrations of acids and bases does matter. So going back again to this scenario, we only had 1 liter of, we said, a 0.5 molar ammonia and 0.2 molar ammonium chloride solution. So had we added, anything over 0.2 moles of solid sodium hydroxide, which, really doesn't take too much, then we already would have overwhelmed, right, our buffer and completely destroyed its neutralizing capacity. And then, so then we're given our effectiveness range. So our buffer is most effective when our acid and base concentrations are 1-to-1, and that's kind of, again, why we start at our Henderson-Hasselbalch pKa point. And then our buffer is most effective, right, when it's in a kind of 10 order of magnitude beyond our base and acid. And then obviously, right, the more moles you have, then the more buffering capacity, but I think that one is pretty self-explanatory. I'll just say more moles. And then again, All right, obviously a concentrated buffer literally has more moles, so obviously more things to react with. And then, all right, again, our buffering capacity is just defined as the amount of acid or base that can be added without causing a large change in pH. And of course, it increases with increasing absolute concentration. And then again, as our base acid ratio approaches 1, then our ability to neutralize both of those improves. And then, of course, you could always tweak your buffers for whatever scenario. So if you're working with mainly acids, maybe you want to have a little bit more base to neutralize that acid, or vice versa, right? If you know that your buffer is going to have to guard against a base, maybe have a little bit more acid. Okay, I don't know if we'll have time for this one, but let's leave off with this one so you can think about it and we can kind of warm up with this one. So what acid would you choose to combine with its sodium salt to make a solution buffered at 4.25? So kind of thinking about that. So like I said, we'll leave off there. We'll pick this up tomorrow so you can start thinking, not tomorrow, Thursday. You can start thinking about how you will approach this problem or start sketching it out. All right, so Tuesday lab people, I will see y'all at 1:30. So same room, 312. You can sit wherever. And so the Tuesday section has more people in it. I want to say there's 21 people signed up for Tuesday and like maybe 8 right now officially for Thursday. So that being said, y'all can always kind of mix and match, right? Or if you miss your Tuesday lab, you're certainly more than welcome to come in on Thursday. And I mean, worst case, we can always squeeze someone in on Tuesday. But yeah, Thursday should have plenty of space. And that'll be good too for lab makeup. So if anybody misses 1 week, we can always like do makeups on Thursday as well or something like that. All right, any last minute questions, comments, things? Yeah, and then, we will just have a welcome quiz on Thursday, so I won't torture you guys with anything. But yeah, like I said, we can always use Thursday as a good review day if people need equilibrium or acid-base refreshers. All right, I will stop this stream unless there are questions, so I'll look for a minute or two. Otherwise, I will see y'all in class on Thursday or in lab, and then yeah, for if you don't attend lecture, just remind me about the quizzes. Again, obviously we just have the welcome quiz, but I don't want to fall behind.